Welcome to Rhizome Network's presentation for the Innovation Challenge, Unlocking Nickel Laterites. This challenge is sponsored by CSIRO, the Commonwealth Scientific and Industrial Research Organization, which we'll learn about more in a few minutes. As part of the presentation, we'll share details about the challenge, why it's important to solve, and types of solutions we're seeking, and how to learn more. We're joined today by members of CSIRO's leadership team, as well as members from Rhizome Network participating in the project. Let's begin with a few introductions. I'm David Kraft, member at large of Rhizome Network. I'm the program lead for this initiative, and I'm joined by Dr. Jared Ford of CSIRO, who is the Critical Energy Materials Mission Leader, Paul Levins, Principal of Beanstalk and an expert in open innovation initiatives, and Dr. Jill Shong, Rhizome Network member and the principal author of the challenge. Thanks to everybody for joining us today. Jared, let's start off with you. Do you want to tell us a little bit about CSIRO and how this project fits in with the overall mission?
Absolutely, thanks. So the CSIRO, or CSIRO as we often call it internally, is Australia's preeminent science organization. We do about $4.5 billion of value add to the economy every year through our science, our network of about 5,500 dedicated scientists and engineers, not only in Australia, but increasingly around the world. And industry is in our name. We have a very clear focus on translating science, getting it out of the laboratory and getting it into industry. And those things happen in 9 different industry-facing business units. I happen to sit in the mineral resources business unit, but we in missions especially are working across these different business units to deliver things like blockchain and other things for the minerals ethical supply chain. Next slide, please. CSIRO is new. It's actually undergoing a transformation program, and we call that program our Challenges and Missions program. And what it is a new way of doing business. We've identified through a lot of our world-leading research into these things, and there's been publications in the last few years around in publications like Nature and also in the Australia National Outlook, which is a signature sort of very long-term modeling piece, where we've identified these grand challenges that exist for Australia. And that's going to be how CSIRO organizes its business going forward. And we have a missions program that sits underneath that. So supporting each one of these challenges is a whole portfolio of missions that are being developed. And these are meant to be, long-term, probably 5, maybe even 7 years kind of a duration, collaborative, and really based on scientific breakthroughs that we can only bring to the market through collaboration with our partners. So one of those missions is the one that I'm leading. It's called the Critical Energy Metals Mission. And our goal at the moment is to create cost-competitive, sustainable battery materials for the world's gigafactories. What we're trying to do in Australia is, because we have tremendous mineral wealth, and in the face of the energy transition, we need to move downstream towards manufacturing to create more jobs and more value in Australia. And the opportunity for us is to really reinvent the way we process many of these materials, things that go into batteries, things that go into solar panels, because those processes are in many cases 50 or 60 years old. And it's time to revisit these, reinvent them so that we can further decrease the carbon footprint of those processes, improve the cost competitiveness of those processes, and then make it capable of Australia, really enable Australia to create those industries here. And that's what the mission's really about. Next slide.
Jared.
Now, nickel in particular is a huge challenge. And if you're paying attention, the latest World Energy Outlook from the International Energy Agency came out yesterday. They put a spotlight on nickel, as well as copper, cobalt, and lithium, as being the key metals that are going to be under extreme demand in the coming years to power the energy transition. So nickel in particular is really important. Our own research, which we released in May, called the Critical Energy Minerals Roadmap, showed that cumulative value of just the metal in nickel is somewhere around $800 billion to 2050. and that that's because all the high-performing batteries are increasingly nickel, high percentages of nickel, and that's projected to maintain, at least for the next decade, that's going to be the majority of demand for nickel batteries that are going to go into high-performance electric vehicle applications. But along with that, because there's so much nickel, you need a lot of the product that actually goes into batteries, which is nickel sulfate, and just making that process, that chemical, that intermediate alone could be 50% of the entire carbon footprint of every little battery cell that goes in your Tesla. And unfortunately, globally, and we'll get into this a little bit later, a very dirty process to turn those laterites in the world into battery chemicals is where the world is headed, because prices are going to rise and make that kind of process economical. So we need to head that off at the pass. And the other thing is that even though battery pack costs are falling, the cathode, the really important and expensive part of the battery, is not projected to fall. And if anything, if prices rise significantly over the next decade because of competition for these metals, it's going to be the last frontier of how we actually reduce the cost of batteries. So nickel in these very high content batteries, which we might see very soon, will be 25% of the cost, and that could rise dramatically. So it's an important issue. This is one of our top priorities as the mission. Next slide. I'll hand it back to David.
Yeah, thanks, Jared. And I think what you've alluded to is there's a lot of movement happening, not just in Australia, but globally around this supply and demand. Do you want to talk about some of that demand and how that's impacting some of these environmental trade-offs and cost of processing that we're starting to see?
Are we headed to Jill or me? Oh, sorry.
Oh, sorry, Jared, that's for you.
Okay. Yep, go for it. So what's really behind this is the EV revolution. So the electric vehicles is where all the new demand for minerals, going to battery minerals, is coming from, and is substantial. So if you just look at the applications, right now the market's kind of dominated by portable electronics and things like that. But automotive products are going to take the lion's share of all new growth in that sector, in the battery sector, going out to the next decade at least. And we feel really strongly as an organization that that nickel-based chemistries in particular, alongside things like lithium iron phosphate, but to a lesser extent, are going to be the key dominant technologies. And that's the problem we're trying to solve in the next decade. Next slide.
Yeah. And over the near term, recycling won't get us there. Is that right?
That's right. And recycling is a tremendous opportunity, but it will not fill the gap. And so new mining is required, particularly. And another factor that we don't think about often is how many of these batteries, after they get used in an electric vehicle, they still have 80% capacity. They could be used for a home storage application or something like that. We really don't know how that market's going to develop. And if that actually happens, then primary demand even increases further for key minerals. So the other thing that's really important that this slide shows is that the world's not finding a lot of new nickel resources. And so this is a chart that showed up in S&P Capital IQ recently, that no new things of any substantial size have been found even since about 2012. And the lower carbon footprint route to nickel products, which is a sulfide starting point instead of a laterite starting point, they're few and far between. And so the prevailing wisdom is that we're not probably going to find any more sulfide mines, and laterites are probably the only game in town.
And was I right, Jared? Is the breakdown between laterite and sulfide? It's about 80% laterite, 70 to 80%.
Yeah. Well, the thing about laterites, I don't come from a mining background originally, but anybody who has some rocky dirt laying around probably has oxide laterites. And that's the problem we're trying to tackle here, is that they get into, because they're so ubiquitous and because prices are going to rise, people are just going to start doing that. And you see that happening in Indonesia at the moment, where there's been 2 or 3 new announcements to develop laterite mines in Indonesia. Now, this is a curve of emissions intensity. So if you look at the embedded carbon, so a ton of CO2 for the ton of nickel contained in a product like nickel sulfate that's going into batteries. The predominant, if you go from a sulfide product or mining operation into the product, it's got a much lower emissions intensity, somewhere around 10 tons of CO2 per ton of nickel that's contained in that nickel sulfate product. But laterites are 2-3 times higher than that. So the real challenge, I think, is that we will be moving in this direction to create things like nickel sulfate that go into batteries from nickel laterites, and we need to reduce the carbon footprint by half or 2/3 in order to bring ourselves in line and reduce the embedded carbon footprint of those key materials that are going into electric vehicles.
Great, thanks, Jared. And I should point out, that there was an amazing amount of research in this challenge that came to us from the CSIRO scientists and commercial partners on this project, and I think it's worth acknowledging their hard work that culminated all this data and background that we have to share. Jill, let me turn it over to you. Would you mind giving us a bit of a mineralogy lesson and talk about these laterite ores and what makes them up and so hard to work with?
Sure, I think, yeah. So the previous slide that Jared showed that showed all the emissions intensity differences for the sulfide ores versus the laterite ores. So clearly the emissions intensity in the laterites are higher and they need to come down, or that is one of the goals of the RFI, or this innovation exercise. But the laterite ores are also harder to process, not just because of the emissions, but because there's some major differences with what's been processed in the past, the sulfide ores. The sulfide ores are located much deeper in the earth than the laterite ores. The laterite ores tend to be closer to the Earth's surface, so they are more accessible by traditional open cut mining techniques. That's the easy part with laterites. But unlike the sulfide ores, when you dig up the sulfide ores, you can process that ore using some methods like flotation. And so it allows you to pre-concentrate the ore before you begin processing it. So downstream processes have a higher nickel content, and that makes it usually a lot more profitable. The second thing about sulfide ores is that when you heat them up, that is an exothermic reaction, and so you are able to recover a lot of energy from processing sulfide ores, and you're also able to get some sulfuric acid out of the process, and so that helps with some of the processing, particularly with leaching mining processes that can use sulfuric acid. So anyway, that's just kind of a difference between sulfide and laterite ores in the processing, and not just the emissions intensity. The laterite ores, and this is where we get into the real challenge, is that they are much lower in nickel concentration than the sulfide ores, and they are also what miners would call, the nickel is widely disseminated, meaning it's distributed through many different types of minerals. The nickel is bound up in iron and magnesium containing silicate minerals, so it's not as easy to pre-process. And so here's this table here just shows you the kind of layers that are in a laterite ore. So the layers depend on their weathering history. So there's the limonite layer that's on the upper part, and then the saprolite layer that's on the lower part. And these differ in their nickel concentrations, where there's more nickel in the bottom layer. but there's also significantly more magnesium in the bottom layer as well, and that can cause a lot of problems because it takes a lot more acid to leach that ore, and so a lot of the challenge of the RFI will be looking how to process the upper layer, the limonite layer.
That's great.
Yeah.
Yeah, so that brings us to sort of the areas for innovation, and what was you shared some of the rationale around pre-concentration and pre-treatment, but do you want to talk a little bit more in depth on each one of these?
Sure. So these are areas where there could be some innovation that could really help with this subject, but there are a lot of advances in artificial intelligence and machine learning, and that is being applied to different mining sites. And so I think that advanced ore sensing techniques are really are needed, and these are techniques that would allow for real-time sensing and sorting of the ore. Now there are some things being done with AI in mining sites, but again, what makes the laterite ores challenging is that they are widely distributed in the ore, and so there's not, it's not just a nickel content that you would need. You would need to be able to correlate that with different mineral types, and so there would have to. I think that there is opportunity in there. I think we all think there's some opportunity in there, but there's going to be some tricky problems to solve with real-time sorting, and AI techniques could be used for pre-concentrating or enriching the ore prior to processing it. So that's one area.
Mm-hmm. And then tell us a little bit more about pre-treatment.
On the second area, that would be more physical or chemical pre-treatments that could selectively extract nickel. And so that could be either leaching processes that selectively extract the nickel from the ore prior to processing it, or pre-treating it so that magnesium is selectively removed. And this would also be a big benefit. Either of those would be really attractive for processing downstream. Anything that increases the nickel content in the ore, and that can only be even if a 10% increase in nickel in the ore would be valuable to this problem.
Right, and as we talked with the industry partners and others, there was, it seemed to me that there was a lot of reception to having one of the two, either emissions or cost, both would be useful in that if you lower processing costs, that savings could be applied to better emissions remediation, or if you could lower the emissions through something that's cost neutral. They weren't necessarily an either or. It's any improvement on those two trajectories would be valuable. Is that right?
Yeah, that's absolutely the case. I think it was made very clear to us during discussions with the industry partners that any improvements in these two areas, in pre-concentration or pre-treatment, would decrease the emissions intensity downstream. So that problem doesn't have to be solved. The emissions intensity doesn't always have to be solved directly. This could really be the key to solving emissions problems downstream.
That's right. Yeah, that's great. Yeah. Thanks, Jim. All right, Paul. Let's bring you in here. You've managed hundreds of innovation projects through your career. I thought a number of the conversations we had with the industry partners were insightful. But do you want to talk us through some of the other considerations and discussions that we had?
Yeah, thanks, David. Look, I think one of the important things to emphasise here is that this is an open innovation challenge, right? At one level, those familiar with that term know that this means sort of allowing ideas and new technologies or feedback, from external industries to your own to flow into a process of thinking about a challenge. But I think it's a bit more than that for the purposes here. It really requires thinking very differently about the problem, and really encouraging a multidisciplinary approach, looking to other industries, doing some analogous sort of thinking about adjacent industries. I mean, even, one of the things that we know about open innovation and why it is helpful is that even the greatest experts are kind of limited by the strength and the power of their own knowledge, right? There's this type of cognitive bias that we all have called functional fixedness. It's a really clumsy term. I wish someone could reinvent it. But it basically means that, we tend to see objects or processes as only working in a particular way, drawn from our own experience. So being an open innovation challenge, we really encourage innovators from other disciplines and other industries, but also those same experts, right, to think about the margins and to explore ideas that they perhaps have mused about and maybe ruled out for whatever reasons. So, what are some of those ideas? What are the, and here we're really using, what I'm really doing here is using, short form expressions as diving boards into possibilities, if we can put it that way, right? So, could you treat nickel like it's the impurity, right? And extract it that way? Is there some sort of centrifugal process that might be helpful here to introduce? Is there gravity separation processes that we might want to introduce here? Can we build on the work that's already been done around magnetics? Jill mentioned AI. There's a spin out that's been built, a startup that's been built off technology out of CSIRO called NextOr, whose sort of flagship product is an on-belt magnetic resonance analyzer, right, that uses a high throughput bulk ore sorting systems. I encourage people to go have a look at that. Is there a possibility of incorporating those sorts of elements? Can particle sorting be improved, right? Spinning off the back of that, can we improve that in some way? Is there some kind of microbial reduction of non-nickel material that we can introduce? Is there microwave, sort of carbothermic reduction roasting processes that have, really been introduced quite recently, coupled with magnetic separation that might be helpful? Is there something from high pressure processing in food? So now I'm just starting to throw ideas out, right?
Just starting to riff.
Right, yeah. But, all to the point here, which is, let's really think broadly about this challenge. Let's really try and rack our brains, because the challenge is all too important not to do that. So I'll leave it there, Dave. That's
great. And one of the things, while we say here patentability is not a requirement, I think it's a nice to have, but it speaks to that point of, if it's new to the industry or it can be rapidly adopted, that is better than having patentability. And of course, as you apply things to, innovations to new sectors or new industries, there's always opportunity for invention. And secondly, and Jared, you might want to speak to this as well as Paul, the plan is to move these concepts and potential solutions into feasibility studies and development. I don't know if either of you want to talk about that process a little bit, but there are commercial partners that have a strong interest in pulling these solutions through to practice. Is that right?
Yeah. So one of the things that attracted us to the process that Rhizome Network is deploying here is that, and our own business sort of insisted that we have 2 industry partners to be directly involved in this process. So we have a global engineering firm and a large nickel producer miner here in Australia that's part of the consortium. And so they've helped us shape this problem definition, and they're very keen partners to take whatever we find here, the viable ideas, and try and move forward as fast as possible towards commercialization. And because we've got these partners on board, and engineering firm is quite keen on expanding their already strong role in the minerals sector. And we've got people with the right attitude. I think is kind of the companies that we've got are keen for change. They know that the status quo is not going to cut it, and they were all in when we said let's do an open innovation challenge around this project. So I feel like we've got the right consortium around the table to actually drive investment in things. And it is the top priority of the mission at the moment, nickel. We're not ignoring things like copper and lithium and things like that, but from our perspective, nickel's probably the biggest problem and probably one of the biggest opportunities for Australia as one of the leading resources of nickel in the world and one of the leading producers already. We need to expand that, and we're trying to build our own battery industry here in Australia as well. So there's a lot of reasons why I think we could move forward fast in the coming months off of some great idea that comes out of this network.
That's great. Thanks, Jared. So for folks that are interested, we are starting to source beginning October 14th, and that will run for 6 weeks, which is a tight turnaround. But I think it's always good to have these projects run under a small sprint. So we are actively sourcing through the Rhizome network. And there are 2 awards from network concepts that are selected, $10,000 Oz for concepts that are selected and moved through. And for new innovators that are watching this, we encourage you to come and sign up through Rhizome Network. Click on the opportunities, and the specific project is the Nickel for Your Thoughts. And if that's not enough, if you need more information or want to know how you can get involved, we do ask that you drop me an email at hello@Rhizome Network, and look forward to seeing you. Well, thanks everybody for your time and participation today. I really appreciate the discussion and look forward to seeing these ideas move through.
Thank you,
Thanks,
David.
David.
Yeah, thank you.
See you soon.
Bye.